the main problem in talking about big infinities is that there's so many of them that the whole discussion becomes incredibly unwieldy. So what we need to do is we need to start with some tools to be able to keep these things under control. And it turns out that the tools are just types of orderings. So you have a set, and you can order it in different ways. And by thinking about the different ways in which we can order a set, we're going to be able to develop these tools that we need to talk about bigger and bigger infinities. OK, so start with a set of natural numbers and consider two different ways of ordering that set. So the first way is the usual way. And now consider this weird ordering where you say the smallest number is not going to be 0. It's going to be 3. That's the smallest. And then after that, things are just as usual. So after 3 comes 0, and then 1, and then 2, and then 4, and then 5, and we just keep going. So a different way of ordering that same set. Now, we know, of course, that the things here are just as many as the things here. But there's another nice feature that these orderings have, and that's that they're isomorphic to one another. So because the sets are the same size, we can establish a 1-1 correspondence between the elements. But in this case, because the orderings are isomorphic, we can establish a 1-1 correspondence which preserves the ordering. So one in which we never have lines that cross. So what we say in this kind of case is that those two orderings are of the same type. So one way I like to think of it sometimes is that they have the same shape. So in both cases, it's an ordering that has this shape. Contrast that with a different way of ordering the natural numbers. So suppose that we say, OK, instead of starting with 0, we're going to start with 1. So 1 and 2 and 3 and so forth. And then what happens with 0? 0 goes at the end. So in this way of thinking of the natural numbers, there is a biggest one with respect to a weird ordering. And that one is 0. And then you can ask questions about it. You can say, for example, well, what's bigger, 0 or 17? Well, 0. You can ask, what comes after 2? Well, 1. But if you tried to ask what comes immediately before 0, then there's no good answer to that question. There is no last thing before 0. But that doesn't mean that the ordering isn't well defined. So in particular, if you take any two numbers, there is a good answer to the question, which one comes after the other in the order, always. And now what happens with this ordering is that it has a different shape. Instead of having that shape, it has this shape. And as a result, the orderings are not isomorphic to one another. So although it's possible to establish a 1-1 correspondence between this set and this set, it's not going to be like this one where the lines don't cross. So instead what you need to do is something like this. You can assign 3 to 0, and then do that. And the lines crossed. So those orderings are not isomorphic to one another. So the only thing that we're going to be concerned about now is not the specifics of orderings, but the order types of order. OK, so here's the first fun thing we can do with order types. let's see how far we can carry out this procedure. So we have this ordering, and then here we extended it because we have, for each position here, we have a position down here, and then we have an extra one. And then, of course, we could add another, and another, and another, and so forth. And then we could just extend it further by having something with the same structure as the natural numbers, followed by another, followed by another, followed by another. And what happens next? Suppose that one wanted to extend this ordering further still.
One of those followed by another like infinitely many times, and then you could take one of those and follow that by one of those and do that infinitely many times and as wanted.
That's right. That's exactly right. So let me add some informal notation, which I'll make precise later. But let's say that each of these guys has shape omega. So then this is what we do. We take something of shape omega, followed by something of shape omega, followed by something of shape omega, and we're going to do that omega many times. And then we can start again. So the minimal extension of this would just be to add one more thing at the end. But of course, as you pointed out, one needn't stop there. So you can add omega many things. And after that, you could, if you wanted, add omega many things. And indeed, you could do this omega many times. And what's next?
You can put another like even bigger dot at the end, and then make that whole chalkboard your whole next omega.
That's right, exactly. So, okay, so we have these big sequences, each of which consists of omega sequences. So we have one of those here and another one here, and then we say, well, add another one here, and keep going, and do that omega many times. And then, of course, one thing you could do is, at the end of all that, add one more thing, and then another, and then another. OK. And the reason this is going to be useful to talk about big infinities is that you can think of this beast as a blueprint for how to extend an initial infinite set. So suppose that the thing at the very start is just some infinite set, say the set of natural numbers. And what happens at the next step is that you take the power set of that set, which we know is bigger. And then at the next step, you take the power set of that. And then the power set of that, and the power set of that, and the power set of that. And then what will you do here if you wanted an even bigger set? So what we have here is an infinite set and a bigger 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 set. And suppose we wanted something even bigger. What do you do? I think Rose knows the answer. Do you want to? Yeah, that's a great idea. That's right. So one thing you can do, OK, I'm going to do this here. OK, so I'm just going to rewrite that first omega sequence. So you start with the natural numbers, and then you take the power set of that, and then the power set of that, the power set of that, and so forth. And we know by Cantor's theorem that each of these has more elements than the previous one. But now suppose you do this. Now what you do is you take the union of all these guys. So in other words, something is a member of this set just in case it's inside one of these guys. This set has to be bigger than any of those. Who can give me a proof? Hint, it's very easy.
So take any set in your original one, then the power set of that is contained in the union.
Yes, that's right, exactly. Exactly, so I'm just going to say what you said again. So suppose not. Suppose that this guy was in fact as big as some member in the sequence, but not bigger than all. So for example, suppose it's as big as that guy. Well, it can't be, because we know that this guy is bigger than that guy. And he includes everyone in there. So this guy needs to be bigger than every single member of the set. So we have something bigger. So you can think of this initial sequence as that first omega sequence. And then you can think of this beast as the first element of the next omega sequence. And if you want to keep going bigger, you can. Then you just take the power set of that guy, and then the power set of the power set of that guy, and using that procedure, construct the second omega sequence. And then at the next limit stage, you take the union again. And following the exact same reasoning, you're going to be able to show that that guy is bigger than everything that came before. And then you repeat with power sets. Yes?
So I just want to make sure I understand all of the notation. So you're saying you're taking the power sets like n times, or like the and this is like the limit as n goes to infinity. Is that correct?
That's right. So what you do is for any natural number n, you include in this set the elements of the nth iteration of this process. So let me spell that out. I'm very pleased you asked this, by the way. OK, so what that guy is this. It's the union of n and the power set of n and the power set and the power set of n and so forth for every member of that sequence. So in other words, this piece contains every natural number and every set of natural numbers and every set of sets of natural numbers and every set of sets of natural numbers and so forth.
So isn't that equivalent to like the nth power set?
The nth power set, so it's going to differ in two different ways. The first way is that notice that although this guy is bigger than that guy, it's not true that every element in here is also in here, because that set consists entirely of sets of natural numbers and therefore contains no natural numbers, whereas this one consists entirely of natural numbers. So each time you progress in this hierarchy, you're actually introducing new stuff. What happens with a union is that it wastes nothing. So whenever you introduce new stuff, it includes the new stuff. So if we were just to take the nth level of this hierarchy, what would happen is that it wouldn't contain the stuff that came before, even though it would be bigger than everything that came before. Whereas here, nothing is wasted. But also, that set contains them all. Whereas if we took the nth set, then like that would be like it would be just like a limited, some finite stage of the procedure, where to get here you need all omega many stages. Excellent. Yes?
So it might be helpful to think about that in terms of the numbers of brackets around things, right? So like on that side, you'll have things without brackets and then things with one set of brackets and then two. And then here you'll have, for any natural number, you have all the things with that many brackets starting it.
Beautiful, beautiful. That's it. That's exactly right. That's exactly right. And in fact, that allows me to ask a question that's going to seem tricky at first, but in fact, that's important to really understand what's going on. So Rose is totally right. So here we have only natural numbers and no sets. So using Rose's notation, no brackets. Here we have sets of natural numbers. So it's going to be things like, OK, so the first member is that guy. The second member is going to contain the empty set, and the set containing only 0, and the set containing only 1, and then the set that contains 0 and 1, and the one that contains 0 and 2, and so forth. So as Rose pointed out, every element in here has one set of brackets. And then the next one is going to contain sets of these guys, so 2 sets of brackets. So here's a question for people. Does that mean that in here we have infinite iterations of brackets? You gave the right answer with your head. Do you want to elaborate? You don't have to. No, he doesn't want to elaborate. No, that's fine, that's fine. OK, no, you want to, yes.
So for any number n, you can go down to the power set here for which you had that many brackets.
Yes. That's right. So what happens here is that for any n, you can find an element which has like n-level nestings of brackets. But crucially, there is nothing in here where you have infinite nestings of brackets. Because everything in here comes from some finite level of this hierarchy. And every finite level has only finite nestings. So it's not that you go from finite nestings to infinite nestings. What happens is that you put together all kinds of finite nestings. Yes?
Why is it a finite number of nestings, like for all of the power sets? I mean, like I don't know what it like an infinite would be, but how does it end?
Right. No, no, no. In fact, it's good that you don't know what it would be because, like in ordinary set theory, it doesn't even make sense. So in ordinary set theory, you can, for any n, you can have any finite n, you can have n-level nestings, but it doesn't make sense to have infinite nestings. That's absolutely right. So this is very vague, but as we progress and build bigger and bigger things, one way to think of it is that the things are going to be wider and wider and wider, and that we're going to consider sets with more and more things. But the particular elements are not going to be that deep, where depth is measured by number of iterations. They're all going to be only, the depth is always going to be measured by some natural number.
I understand that like that's how it works. That's how we can like use the union. But I'm saying like, if you're going through every element in omega and the first one is the natural numbers, and the second one is the power set of the natural numbers, and you keep on doing that with that pattern, why would you not end up with like an infinite power set? The power set like infinity times. How does that end? So you can take the union of that, and it's still finite somehow. That's what I'm asking.
Yeah, no, these things are weird. So I think that, I mean, if one starts thinking about it intuitively, then there's definitely room for that kind of thing. But I think what happens is that mathematicians have slowly like realized what kinds of things work and can be properly defined and which ones can't. And what can be properly defined is this. So what can be properly defined is you say, look, I'm not saying anything about limits of any kind. All I'm saying, I'm going to tell you what the nth member of this sequence is for n, a finite number. That's what I'm going to say. And for each of those, it's well defined. Of course, it's true that there are infinitely many of those, but each one lives at some finite stage. So like, if you want to give a full description of each one, all you need is finite iterations. And then you say, OK, now I'm going to tell you about some other beast. And it's not quite that this beast is something like the infinitive level of this hierarchy. It's a different thing. It's the result of taking each of these, all of which were built at some finite level, and putting them together. So really, you have two different kinds of operations. You have the power set operation, which always happens one step at a time, and where where it never makes sense to have a sequence of this kind, where instead of having n times, you have infinitely many times. That never makes sense. That's one kind of operation. And then you have a second kind of operation, which is just to take a bunch of sets and pull together their members. And using those two operations, we're going to be able to build very, very complicated beasts. And in particular, beasts as complicated as those. OK, so before I get back to constructing this beast, does anyone have any other questions about how this construction works? OK. So here is one way in which one can use this plan to generate a truly enormous set. So what you do is, within these little omega sequences, to go from one item to the next, you apply the power set to what you had before. And then at limit levels, in other words, what you do when you have an item that comes after an omega sequence, what you do is you pool together the members of everything you had before. That procedure is going to guarantee that at each point of that order type, you have something bigger than what you had before. So we started with the size of the natural numbers, and then the size of the real numbers, and then something bigger, and then something bigger, and something bigger, and then something bigger than all those, and bigger, and bigger than all those, and bigger, and bigger, and bigger. You put all those together, and you have something bigger than all those, and you can still go bigger, and bigger, and bigger, and bigger, and so forth. So here is the lesson of this. The lesson of this is that given that we're equipped with these two operations, power set and union, the task of finding big infinite sets is just the task of finding orderings, which are longer and longer. And that is why the study of large infinities is, in effect, the study of order types. OK, so that was the informal version of the story. Now, at this level of sloppiness, we basically cannot get much further than what we've done. So like, I've drawn a picture. I've done my best to draw a picture that's intelligible. But like at some point, pictures are not going to do. At some point, we're going to need some like proper notation to talk about these orderings. So that's what I'm going to do now. OK, everyone on board on what's going on? OK. So I've been sloppy about a bunch of things today so far. The first of which is that I've been talking about orderings and order types, but actually, the only order types that we're going to focus on here are order types of a very special kind, are the types of so-called well orderings. So I'm going to start by telling you what a well ordering is. So well orderings are a special case of linear orderings. And I'm sure many of you have heard of linear orderings, but the basic idea is that a linear ordering orders a set in such a way that they all form a big line. So that means, in particular, that we don't have any loops. So whenever happens that, so for example, this is something that could happen. So suppose you have this weird ordering where you say A is bigger than B, and B is bigger than C, and C is bigger than A. So that's a loop. That is not a linear ordering. In a linear ordering, that doesn't happen. Another thing that happens in linear orderings is that any two things are comparable. So if you take any two elements of the set you're ordering, there's always an answer to the question, which one is bigger than which one? Can anyone give me an example of a way of ordering a set where that's not the case? So where you have an ordering of some kind, but it's not the case that any two elements can be compared by using the ordering. So where sometimes you say, OK, who's bigger than whom, according to this order? And you say, well, there's no good answer to that question. Yes?
I guess the answer would be what you had done in the first example, where you put the 0 all the way at the end. And who is bigger than who? Well, 0 is less than who. Or 0 is greater than whatever, who.
I'm glad you bring this example up. I'm glad you bring it up, because look. So here's that ordering. So there is something that ordering doesn't answer, and you're certainly right about that. So what it doesn't answer is who comes immediately before 0. So that's the wrong question to ask for this ordering. But here is a question that will always have a good answer for that ordering. Take two numbers, any two you want, and ask who's bigger than whom, according to this ordering. For that, there's always an answer. Because if you pick 17 somewhere in there and you say, who's bigger? Well, 0 is bigger. You pick a Google plus 1 and you say, who's bigger, a Google plus 1 or 0? 0, and so forth. So all that's required in order for something to count as linear ordering is that second kind of question always have a good answer. So if you pick two elements of the set, you can always say who's bigger than whom. OK, but there's some ways of ordering things where that's not true. There's some ways of ordering things where you can pick two elements of your set, and you say who's bigger than whom, and that doesn't make sense. So a hint is think about trees. Yes?
So if you think of something like a directed graph, everything that's the same number of steps away from the node of the tree would be incomparable, but anything along the path you could compare it to elements as the distance from the node.
So here's a version of that. Suppose that you have a tree. And let's just look at the nodes of this tree and just define an ordering. So say that a node here is bigger than a node there if you can go from the bigger one to the smaller one by always going up on the tree. Then, these guys are definitely going to be comparable. So this one's bigger. But now suppose you say, OK, who's bigger? Him or her? Well, our definition doesn't cover that case. So this ordering is going to be a partial ordering, but it's not going to be linear ordering. What about the integers? So including both positive and negative integers. So are those linear ordering? Yeah, those are fine. Those are fine. What about this? This is a slightly, so take some set A. So say that A is 1, 2, 3, and take the power set of A. And then say that if X and Y are in the power set of A, then X is smaller than Y if and only if X is a subset of Y. Is that a linear ordering?
So you can just take a singleton set of 1 and a singleton set of 2, none of which is a subset of the other.
That's right. That's exactly right. That's exactly right. So using this definition, some sets are going to be smaller than other sets. For example, because that guy is a subset of that guy, then one singleton is going to count as smaller, given this ordering, than the set of 1, 2. But as he pointed out, if instead you tried to compare the singleton of 1 and the singleton of 3, because neither is a subset of the other, they're not going to be comparable. OK, so in a linear ordering, any two things are comparable. We're also going to assume transitivity. So we're going to assume that if one person is smaller than another and that person is smaller than a third, then the first one is smaller than a third. And we're also going to assume that nobody's smaller than herself. OK, that's the definition of linear ordering. This, by the way, is one reason why it might be useful to go to the notes. So this isn't going to be that important in practice, but if you want to make sure you're totally clear about the definitions, go to the notes, and everything is going to be clearly defined there. OK, so we have linear orderings. A well ordering, and here I'm going to write down the definition. So a well ordering less than of a given set A is going to be a linear ordering with a certain additional property. The extra property that if you take any non-empty subset of A, any one you want, it's going to turn out to have some element that counts as the smallest element of that subset according to the order. So the canonical example of a well ordering is the standard ordering of the natural numbers. So it's definitely a linear ordering. And if you take any set of natural numbers you want, any non-empty set, it's going to have a smallest element. In fact, one way of axiomatizing arithmetic is by having that principle be one of the axioms. Can anyone, well, here's an example of a linear ordering that is not a well ordering. The integers, including both the positive and the negative and the non-negative integers. So there are the integers with their standard ordering. who can give me a non-empty subset of that set that won't count as having the smallest element, given the standard ordering?
The set of negative integers.
Correct. So just take the set of negative integers, and you say, who's smallest? Well, nobody is smallest, because whoever you pick, that person minus 1 is going to be even smaller. OK. So I want another example of a set which is not well ordered. In fact, I'll be happy either with another example of a set that's not well ordered or with another example of a set that is well ordered. I just want examples.
The 1 over 2 to the n set, like when you're stepping from A to B in distance, so you'd have 1, 1/2, 1/4. Yeah.
Good, nice. OK. So 1, 1/2, 1/4, and so forth. No 0. And then that definitely is not a well ordering, as evidenced by the fact that if you take the entire set, that set does not have a smallest element. Good. Now, can anyone do this? This is going to be useful. Can anyone take the integers, which we've seen are not well ordered, but define a weird non-standard ordering for that same set, which is a well ordering? So in other words, can anyone give me a well ordering of the integers? Yes?
If you start with 0 and then +1, -1, +2, -2, and so on.
Excellent. That's right. That weird ordering of the integers is a well ordering. Now, what about the inverse? So can anyone start with the natural numbers and give me a weird ordering of those guys, which is not a well ordering?
Could you just go backwards?
Yeah, great, great, great. So that's a linear ordering, but it's not a well ordering. What about the rational numbers? Are the rational numbers well ordered? In fact, let me make it a little bit harder. So are the non-negative rational numbers well ordered?
They're not well ordered because you could have the set from 0 to 1, non-inclusive 0 and 1, and there would be no smallest element.
That's exactly right. That's exactly right. They also, by the way, contain this set. Which is also a counterexample. Well done. OK, so this is what's happened. So what we've done is we've looked at a particular kind of ordering of a set, which is a well ordering, of which the basic principle is this one. And the basic tool we're going to use to talk about big infinities is to think about types of well orderings. And what's cool about well orderings is that they can be organized very, very neatly. So I'm going to give you an exhaustive list of the well orderings. So I'm going to show you the shapes of all well orderings, or at least the first few, but you'll see the pattern. So the simplest well ordering of all is the trivial ordering of the empty set. So the empty set has nothing, so there's nothing to order, so you don't have to say nothing. Trivially, if you take a non-empty set, whatever you want is true, because there's going to be no non-empty subset of the empty set. OK, so here is the shape of the empty well ordering. There. Okay, that's the simplest of all. Now, the next simplest is the well ordering of a set with a single element. So the shape of that well ordering is just that. There's only one element, and there's no need to compare her with anybody else. All there is her. And then if you have a set with two elements, every well ordering is going to have that shape. There's going to be one, and then there's going to be another. Of course, that doesn't mean that you can only well order a set in one way. It's just that any two well orderings are going to have the same shape. So for example, take the set 1, 2. That could be well ordered like that, and it could be well ordered like that. And of course, it can make a big difference. For example, if the ordering is, if these are like someone's children and the well ordering is like who's the favorite, then that can make a huge difference. But both of these well orderings have the same shape. It's the shape first one and then the other. And if you take sets of 3 elements, then the only type of well ordering you're going to have is one and then another and then another, and so forth. So for sets with finitely many things, there's going to be exactly one kind of well ordering, and it's exactly what you would think it is. But things get interesting when we move to sets with infinitely many things. So the smallest infinity is the infinity of the natural numbers. And there are many ways of well ordering that set. There are many shapes that a well ordering of that set could take. So the first, the simplest well ordering of that set is that one. But as we've seen, there is a well ordering of that set that has a different shape. Same number of elements. It's just that that's a different kind of well ordering for that set. And then this one, and then this one, and so forth. And now you can start to see what's so awesome about well orderings. The thing about well orderings is that any two well-ordered types are such that one is an initial segment of the other. I'm going to write that down because it's so cool. The reason that's so cool is because it means that we can order the well-ordered types. Because you can just say, if you have two well-ordered types, you can say that the smaller one is whichever one is an initial segment of the other. So you can say that, for example, you take these two, you can say that that one's smaller because this one is an initial segment of that. And if you take this one and that one, you can say that this one's smaller because it's an initial segment of that one, and so forth. In fact, it's not just that the well-ordered types are ordered by the initial segment relation. They are well-ordered. So the well-orderings form a well-ordering. And that is our trick. Because the well-orderings are so well-behaved, what we can do is we can supply a theory of well-orderings. And we're going to develop bigger and bigger well-orderings. And each well-ordering is a blueprint for an enormous set. OK, so that's the plan for next time.